Hello everyone, and welcome to Lecture 2 in the Introduction to Molecular Simulations lecture series. This lecture is going to be about the first branch of physics that we're really going to rely on to understand molecular simulations, and that is classical mechanics. Here, Lecture 2, Classical Mechanics. So inevitably, the types of systems that we're going to be interested in are going to contain somewhere on the order of 10 to the 24 atoms and particles, all interacting all at once. However, before we start to study these really complex and large systems, we need to first understand how to model just a single particle. And within classical mechanics, the equation that you've known and studied since you were in high school is the Newton's equation of motion. So this is where we're going to start. First, we're going to say that a particle is an object with a position given by a vector in some predefined space. We'll call it R of the particle I with non-zero mass Mi. Now, a particle in classical mechanics can be thought of as essentially just a point that we can describe its position by directly with what this vector is here. And even though it's a point that technically doesn't take up any volume, it still has a non-negligible mass, Mi. Now, within classical mechanics, the motion of these types of particles is governed by Newton's equation of motion. Newton's equation of motion. Newton's equation of motion. And this is an extremely important equation for molecular simulations and for this course. And essentially, you have your force. This under squiggle notation I'm using signifies that this is a vector. The force on particle I is equal to the mass of particle I times the acceleration of particle I, where the acceleration is defined as the second derivative of the position of I with respect to time. So this is the governing equation of motion for a classical particle. So let's move on to a quick example. All right, so let's do our first example. We'll call this example 1. Classical motion under no net force. Under no net force. So let's write Newton's equation of motion for a particle that's experiencing no net force. Well, we have F net on particle I is 0. Newton's equation of motion is then 0 equals the mass of I, d squared, the position of I, dt squared. This guy can get divided by on each side, and we are left with this simple differential equation, which you can solve by integrating both sides. So we'll integrate both sides with respect to time. And in the first one, we'll get some constant here. So we'll have C1 is equal to the integral of the derivative of something is just antiderivative here. So we have this. So this is sort of step 1. Step 2. Let's take the integral of both sides again with respect to time. t. And now we're going to have, on the left-hand side, c1t plus some constant c2 is equal to r of t. So the position of the particle, r, as a function of time, is just a line. So you can see this is just y equals mx plus b, or mt plus b. So c1 is the speed at which the particle is moving, and c2 represents where the particle starts. So essentially, when you have no net force, your particle will just continue moving in a straight line. All right, so now that we understand the very basics of how Newton's equation of motion works, let's look at a definition for work. Work. What is work? Work is defined as the dot product between a force and a displacement of a particle, and a displacement. Mathematically, we can express this as the work is equal to a force dotted by a displacement. Now, notice we have the dot product here because we have a multiplication of two vectors, and the work is a scalar quantity. So by taking the dot product between the two vectors, we recover a scalar. Now, if the force is changing over the course of this displacement, we actually need a more precise formula for this, for the work, in which we invoke an integral over the path that the particle takes. So in this case, in a more general case that we're going to stick with, is that the work is defined as the integral of the force dotted by these displacements added up over the path of the particle that it takes. Now, these equations can actually be thought of, they're similar in certain instances, but the way that I like to think about them is, suppose you had some particle and you have some displacement of that particle so going from r to r plus delta r. This first equation here would compute the work as if you moved in a straight line between these two. The second equation, depending on what path the particle takes, is actually just adding up a set of differential displacements of these f dot drs, so these little drs. It's adding these up along the path until we get to our final point. And you can imagine if there were aspects of the force that were changing in time or in position, and the force was non-conservative, which we'll discuss here in a second, that these could actually give you different quantities. So we need to be careful, and generally we're going to think of work as being defined by this integral equation. Well, now that we understand the definition of work, we can start to look into how to invoke the definition of work and Newton's equation of motion to define important quantities like the potential energy and kinetic energy. All right, let's talk about the potential energy. You're probably familiar with the potential energy in some respects, and you've probably used it before in your physics classes. But we're going to look at a very fundamental picture of what potential energy is based on Newton's equation of motion and work. So first I want you to suppose that a force acting on a particle is a function of position, and moves along a closed path Now, what is a closed path? Well, we can draw a closed path like this. Suppose our point starts at some point A, and it begins to move through space through some point C to another point B. Now, for the path to be closed, from B, it has to move back through some arbitrary point D all the way to A. So you can see this is a closed path because we're starting and ending in the same place. Now, usually when we're writing integrals over a closed path, we're going to use a little notation where we'll say, okay, the integral sign over a closed path. We'll give it a circle in the middle of the integral, and that indicates that we have an actually closed system. So when we write the work that the particle experiences as it goes through this path, we will write it as the work is the closed path integral of f dot dr. Now, we're going to introduce a definition here. If this integral is equal to 0, then f is equal to fc, where c indicates that f, or this force, is conservative. Force is conservative. Is conservative. So by the definition of a conservative force is that if a particle goes through a closed path and you calculate the work and it equals 0, then the particle is moving in a conservative force, or under a conservative force. All right, so returning to our closed path, now I want you to consider what happens if we break the motion of this particle through this path into two parts. Let's break it into a first part in which the particle goes from A to C to B, A to C to B, and a second step in which the particle goes from B to D to A. So two separate motions to complete this closed loop. Let's express the work on the particle in terms of these two separate paths. So we know that the work is just going to be the force dotted with the displacement integrated over the paths. Since the integral is linear, we can actually just split the integral up. So we're going to have the integral, the work integral over this path plus the integral over this path. So that'll give us something like this. We'll have the work from A to C to B of f dot dr plus the integral from B to D to A of f dot dr. This is the total work. And these are just the work from A to C to B and the work from B to D to A. Now I want you to consider what happens if we take the second path and we reverse it. We reverse the direction. So we're going to call this 2'. Imagine we took this path and we flipped it. So instead of going from B to D to A, we're now going from A to D to B. What happens to the work in this one? So we have here the work, this is the work for path 1, this is the work for path 2. Now what is the work for path 2'? Well, because all we've done is changed the direction of the motion, that's only going to influence the sign of our dr. So our work of 2' is just going to be the minus work of 2. So this is the minus work from B to D to A. Maybe it'd be more precise here. Instead of writing this, we'll say the work from A to D to B is just the opposite sign of the work from B to D to A. Well, what we can do then is we can substitute this into this original equation, and we find that the total work along the closed path is just equal to the work from A to C to B minus the work from A to D to B. Now, what happens if the force is conservative? If the force is conservative, we know by definition that the total work has to equal 0. If that's the case, and this equals 0, here I'll write it. If this is equal to 0, we now have a relationship between the work of the path that goes through this point and the path that goes through any other point. And in fact, we can just write directly that the work from A through some other point to B is equal to the work from A to D through some other point D to B. So in a conservative force, the work is the same going from A to B no matter what path you take. What that means is that the work required to move against some conservative force field is the same no matter what path you take. In fact, it's independent of how you get there. It only matters that you got from A to B. Now, this is a really important point. And what we're going to do is say, okay, we can drop these arbitrary points that the path goes through, and we're going to define potential energy as this work that it takes to get from A to B independent of path. So I'm going to write it here. The potential energy, and we're going to call it psi, from A to B is defined as the work that it takes to go from A to B. And of course, this is in a conservative field, for a conservative force field. Sorry, the writing got a little scratchy there at the bottom. Now, what's so cool is that if we know psi, if we know this function for any r, all we need to do is plug in our initial and final points, and we can calculate the potential energy. So the goal here was to essentially motivate just from the definition of work that we could actually extract information about the potential energy and give a rigorous definition of this concept. So now you may wonder, how can we compute the relationship between the potential energy and the conservative force? Well, what we'll do is we'll look at the work required. So we're gonna quantify the work required to move the particle, by an infinitesimal displacement. Infinitesimal displacement, dr. So the idea is we have the particle at r, and we're going to displace it by that little infinitesimal dr to give us r plus dr. And we want to quantify the work in this process. Well, the work is just the work from r to r plus dr. But we know that this is independent of the path in a conservative field. So let's suppose, rather than going through just dr now, we're actually going to go through an additional point A. So we'll start here, and we'll say, okay, we're going to go through some other point A on our way to r plus dr. Now, remember, this is fine, right? Because of what we showed last time, it doesn't matter what points we move through in the path. It only matters that we move between the start and end points. Okay, well now this work here, so we'll say this is 1 and this is 2. The work for 1 was this. The work for 2 now is the process of going from r to a to r plus dr. Well, just as before, we can split this into two paths. We can say this is the work from r to a plus the work from a to r plus dr. And then, of course, we can flip this, as we saw last time, by just reversing the direction of the path and changing the sign. So this term is the same as the work from a to r plus the work from a to r plus dr. Well, we now have our definition we can now invoke our definition for the potential energy. So this is just going to equal minus psi from a to r plus psi was the potential energy, from a to r plus dr. So this was our total work. Now I'm going to rearrange this. Minus psi of a comma r. This is equal to the work. Well, what does this look like? We have a function at a infinitesimal perturbation minus a function without the perturbation. Well, it looks kind of like we're starting to get towards the definition of a derivative. If we think of what the definition of a derivative was, we would simply divide this by dr and take the limit as dr goes to 0. However, when we have these sort of situations in classical mechanics, a lot of times what we're going to do is actually invoke a Taylor expansion and try to write this in terms of a Taylor expansion. So when we do that, we can see that essentially this term, this ya at r plus dr, is equal to a Taylor series in which we have no perturbation plus the first derivative times the r that you're at, or the dr, plus the second derivative with 1 over 2 factorial, etc. And I think what I'll do is I'll post an additional video with a side on Taylor expansions, but for now, just trust me on this. This is going to equal here the derivative of psi with respect to r, evaluated at r, times dr, plus a series of higher order terms that come out of the Taylor expansion. And what we're going to do is assume that these are small and perform something what we refer to as a linear approximation. So this is a linear approximation of the Taylor expansion. A linear approximation of Taylor expansion. Now this is kind of interesting. What we're seeing is that the work is just equal to this derivative dotted by dr. Well, what does this kind of look like? Well, we know that the work, it looks like I'm running out of room here, but I'll write it here for now. We know that the original definition of work was the force dotted by a displacement. And of course, we integrate over all the drs, but in this case, we have one dr. So this is sort of the first definition I wrote, but we still have the infinitesimal displacement. But if we compare our definition for work with what we have now, and I think maybe let me rewrite this. Let me rewrite what we have now in a more clear way here. What we just derived was that the work is equal to d psi dr evaluated at r dot dr. So what does that mean? Okay, if we compare these two equations, we can see that it appears that this d psi dr is f. So f is equal to d psi dr. Now, this is the work required to move the particle by some dr against a conservative force. So, the true force that the field is exerting on the particle is in the opposite direction. So what we can actually do is we can write that this conservative force here is equal to the minus derivative of psi with respect to r. And this is a really important equation. And to be super clear, now, this r we've written in a very general way, so it could be in Cartesian coordinates, spherical coordinates, whatever coordinate system you care about. And the way we express that mathematically, or the way we can express this equation mathematically in a more concise way, is that f is equal to the minus gradient of psi. And this is the relation that we're going to care about. So notice all we did was we investigated the work as we moved from some r to some r plus dr. We broke it up into another path, which we knew we could do by what we talked about just a few minutes ago. And by rewriting this work out in a clever way, we can actually extract that the conservative force is equal to the minus gradient of the potential energy function. Now, this is going to be really important in molecular simulations, and this is how we're actually going to calculate the forces that are interacting, or that the particles are experiencing in our simulations. But this is a really important result. We should star this one. All right, so we've just seen that by only looking at the definition for work and the paths that particles take, that we could extract interesting information about the potential energy and also how it's related to a conservative force. Now let's turn our attention to the kinetic energy, which you've also probably heard of before. But let's not just take for granted what the kinetic energy is. Let's actually try and figure out where it comes from. And the way we're going to do that is we're going to calculate the work required to change the velocity of the particle. Required to change the velocity of a particle of mass m1 from its initial velocity, v1 at time t1 to final velocity v2 at t equals t2. Now, immediately we need to think about what's going on here with respect to the Newton equation of motion. So we learned in our first example that if we had no net force on the particle, that the particle would continue to move in a straight line at the same velocity. But now we actually have a change in velocity. So what that means is that we now have a force. There is some force being exerted on the particle to change its velocity. In this case, we're going to compute the work, integral f dot dr. But now what we're going to do is we're going to actually substitute Newton's equation of motion into this integral. Newton's equation of motion. And what that's going to give us is a new integral in which we have the mass of the particle, and I guess we called it m1 here, times the acceleration of the particle, dt squared, dr. Now our integral is still with respect to r here, and so we need to do a change of variables. How should we think about this change of variables? Well, we have r going to dr, But how does this happen in time? Well, one way we can think about this is that at r there's some velocity, and that velocity is given by dr dt. The particle is moving. Well, if the particle's moving in a specific direction with a certain velocity, and let's say it's in this direction towards the dr, then the distance that's traveled is the velocity multiplied by how much time it's traveled. So we have the velocity here is dr dt, and the distance traveled is the velocity times how much time has passed, which if we're doing an integral with respect to time, which is the variable we want to change into, is dt. So when we change the variables, we're actually going to introduce dr dt dt. Now what that's going to give us now with our change of variables, is a new integral in time, and we can say it's from t2 to t1. Remember, we're looking at the difference in velocity from t2 to t1 of m1 d squared r dt squared times dr dt, this is our change of variable formula, dt. I'm just going to rewrite this equation. Integral from d r dt squared dot dr dt dt evaluated from t2 to t1. Now, to make some progress here, we have to notice something kind of interesting about this, this integrand here. So the m1 is a constant. We don't need to think about it too much. But this d squared r dt squared dot dr dt can actually be rewritten. And the way we're going to rewrite this is as d dt of dr dt dot dr dt, and there's going to be a 1/2. And I'm telling you this, but let's show it really quick and make sure that this makes sense. So when we take this derivative here, we're going to use the product rule. So our first derivative, we're going to end up with dr squared dt squared dr dt plus, now from the product rule, dr dt times d squared r dt squared. Right? And this is all multiplied by 1/2 is what I'm claiming. Now, we can just rearrange these guys and add them together, and what we find is that this inside the brackets, we have 2 d squared r dt squared times dr dt times 1/2. The 2's cancel, and we're left with our integrand. So now that we have that, we can rewrite this integral, integral t2 to t1 of m1, 1/2 m1 d dt, let me make this bigger, d dt of dr dt dr dt dt. Now that we've done this, I'm just going to erase this so I can have some extra space. It's kind of tricky to manage the space on this single whiteboard. Well, now that we have this guy, let's think about what this is. These, of course, are the velocities, right? So we can actually rewrite this, and I think maybe I should remind you that this was the work required to change the velocity of the particle. So this work is now equal to, and I'm going to bring the m1 out of the integral because it's a constant, t2, t1, and I'm going to insert definition for velocity here, dt. What happens when you take an integral with respect to a variable of a derivative of something with respect to the variable? Well, the fundamental theorem of calculus says that it's pretty easy to do that. We just take whatever this guy is as our integrand. As our solution. So we're going to have v dot v evaluated from t2 to t1. Well, what is this? This is just 1/2 m1 of v2 squared minus v1 squared. So as the velocity changes from v1 to v2, we have a change in work or a change in energy corresponding to 1/2 m1 v2 squared minus v1 squared. What we're going to do is define this intrinsic property. We're going to define the 1/2 mv squared, this property of the system, as the kinetic energy. So Ke is 1/2 mv squared. And this is the formula that you learned in your high school physics classes. And you can see, basically, all we had to do was define work and look at Newton's and define Newton's equation of motion. And from those equations, we can get to these intrinsic properties that you've learned about in the past. So now that we've defined potential and kinetic energy, let's explore the concept of the conservation of energy. Conservation of energy. Conservation of energy. We're going to consider a particle moving in a conservative force field, moving under a conservative force, which, if you recall, is equal to the minus gradient of our potential energy function. And an external force. Now, F external. We want to calculate the work done by F external on the particle. Calculate work done on the particle by F external. All right, let's calculate it. We know the drill. The first thing we're going to do is write down what the work is. The work is the integral of F dot dr. What's F? Well, let's invoke Newton's equation of motion. We have our particle of mass m, dr d squared r. Mass times acceleration is equal to the net force on the particle, which was the minus gradient, this is our conservative force, plus our external force. Now we want the external work, the work from the external part of the force. So what we're going to be able to do then is move this to the other side and plug this into the equation. So we have simple addition here, F external. And of course, this is also a vector. I should make sure to write that. So we have this, plugging that in to our integral. We obtain m d squared, what am I missing? I wrote this wrong. dr d squared t. There we go. Sorry about that mistake. dt squared plus psi, gradient of psi, and this is the integral over r still. Just as last time, we need to do our change of variables, t2 to t1. And we're going to then look at m d squared r dt squared plus psi y. And now we did our change of variables, which you remember last time was just the velocity times the amount of time that the particle has moved. Well, we've already solved these equations, so we're not going to go into a ton of detail. We're going to say this is equal to, we know from this part of the term that we just calculated that this is 1/2 m v2 squared minus v1 squared, right? And here we have the gradient of psi dot dr dt integrated over dt. So let's think about what that means. We have essentially for this term, it's a little bit tricky, but once you see it, it's not a problem. I'm gonna write it up here. Gradient of psi dr dt. Let's think about what that means. Well, it's essentially d psi dr dt. What does this look like here? Well, this to me looks like a chain rule d dt psi, which is a function of r, right? Because if we take d dt of psi r, then what we end up with is the d psi dr term times the dr dt term through the chain rule. Well, if we can write it like this, then this part of the integral here, so let's see, I'll write it here. The integral from t2 to t1 of d psi dt, fundamental theorem of calculus, is just going to give you psi at t2, psi minus psi at t1. And of course, it only depends on the position. So psi at t2 is at the position r2 and at the position r1. So what that's going to give us is plus psi when it's at position 2 minus psi at position 1. Okay, well, let's group like terms together. So what we're going to have here is that the work due to the external force is 1/2 mv2 squared plus psi at r2, so whatever the potential energy is at the new position, minus 1/2, get brackets here, minus 1/2 mv1 squared plus psi of r1. Now, by grouping like terms like this, we're actually going to create a new definition. We're going to say that the kinetic energy, the Ke, plus the potential energy is equal to the mechanical energy, Me. Mechanical energy. So essentially, if there's some external force that's impacting the system, the change in the energy of the system is going to be related to the difference in the mechanical energy at the final state minus the initial state. Now, if the work external or the external force is 0, then this is 0, and that means that the mechanical energy is equal in the initial and final states. Because that's the case, we say that the mechanical energy, E, is a constant of motion. So basically, by showing here that the work done by an external force is this difference, and if there is no external force, that essentially the mechanical energy doesn't change between the initial and final states, we call this a constant of motion. Constant of motion. So the mechanical energy is a constant of motion. And generally, we're going to write that, and I'm just going to create a little spot here really quick. Just have to have time to write this down. This work, external, is equal to the change in the mechanical energy, and we're going to call that E. When this is 0, the change in energy is 0, and we have that the energy is a constant of motion. So in this lecture, we've seen how to define potential energy, kinetic energy, and understand the conservation of energy only using the definition of work and Newton's equation of motion. The last thing I want to talk about is the extension of classical mechanics, to many particle systems. What's really great about Newton's equation of motion in a many particle system is that it still holds for each particle in the system. We just have to write it for a specific particle I, for I being the number of particles in the system. Before, with our single particle, we were able to define the state, or the mechanical state, by two variables. The mechanical state was the position and the velocity, or the momentum, depending on how you want to write it and what type of formulation of classical mechanics you care about. But for our single particle state, we could define it by R and V. But when we have n particles, so n particles, our mechanical state is now the positions of all of the particles simultaneously and all the velocities simultaneously. So the space has just grown pretty substantially when we've gone to this type of system. Now, the only, and I'm not going to go into detail on this in this lecture, but the only difference between this many particle system and the systems we've talked about before is that now there is a new force, there is a new conservative force, which we are going to call phi, which is a function of the positions of all the particles. And this is going to be defined as the interaction term, the interaction potential. Well, and I need to be more precise. This isn't a force, this is a potential energy. So the new conservative force is the minus gradient of this term. And in that case, if it's the minus gradient, then it is the interaction force, and phi is the interaction potential. Now, that phi is really important because in a molecular dynamics simulation, when you're dealing with many particles all at once, they're going to be interacting via some interaction potential in general. So that concludes the lecture. Next time, we're going to be talking about the ways to solve Newton's equation of motion numerically, because when you have multiple simultaneous Newton equations of motion, there will be instances in which there are no analytical solution, and we need to invoke numerical methods in order to approximate the solutions. Well, thank you very much, and we'll see you next time.